NENOMATICA, where mathematics meets YouTube excellence. In this example, we will find all real values of m that make the quadratic expression a equals x squared plus m times m minus 1 times x plus 36 a perfect square trinomial. A quick reminder, a perfect square trinomial has a repeated root. Equivalently, it can be written as left parenthesis x plus right parenthesis squared. That means the discriminant must be 0. Now identify the coefficients a, b, and c for our quadratic. Here a equals 1, b equals m times m minus 1, and c equals 36. Set the discriminant b squared minus 4 ac equal to 0, and substitute the values. Case 1, m times m minus 1 equals 12. Expand and factor to solve for m. Case 2, m times m minus 1 equals negative 12. That gives m squared minus m plus 12 equals 0, whose discriminant is negative, so this case has no real solutions. As a neat verification, if the expression is a perfect square, then it matches x squared plus 2ax plus a squared, because a squared equals 36, a equals plus or minus 6. With it equals 6, 2a equals 12, which matches when m equals 4 or m equals negative 3. Substitute m equals 4. The middle coefficient becomes 12, and the trinomial equals x squared plus 12x plus 36, which is x plus 6 quantity squared. The same happens for m equals negative 3. To summarize, the valid m values are 4 and negative 3. Let's place them on a number line to cement the result. Final answer. The quadratic is a perfect square trinomial exactly when m equals 4 or m equals negative 3. In this example, we will find the value of m that makes the quadratic expression a perfect square. Our expression is a equals x squared minus 2 times open m plus 2 close times x plus 12 plus m squared. Key idea. A quadratic ax squared plus bx plus c is a perfect square exactly when its discriminant is 0. That is, delta equals b squared minus 4ac equals 0. For our expression, the coefficient a equals 1, b equals negative 2 times open m plus 2 close, and c equals 12 plus m squared. We now set the discriminant equal to 0. Substitute a, b, and c into the discriminant. We get bracket negative 2 times open m plus 2 close bracket squared minus 4 times 1 times open 12 plus m squared close equals 0. Square the first term and distribute the 4. That gives 4 times open m plus 2 close squared minus 4, m squared minus 48 equals 0. Expand open m plus 2 close squared into m squared plus 4m plus 4. Then distribute the 4. Combine like terms. The 4m squared and negative 4m squared cancel. We are left with 16m minus 32 equals 0. Solve for m. Add 32 to both sides and divide by 16. 16m equals 32, so m equals 32 over 16, which is 2. Quick check. Substitute m equals 2 back into a. We get x squared minus 8x plus 16, which factors as open x minus 4 close squared. That confirms it is a perfect square. Final answer, m equals 2. In this example, we'll determine all parameter values that make a quadratic have a double root using the discriminant equal to 0 method. Here is the problem. A quadratic in x has a double root exactly when its discriminant is 0. The discriminant is b squared minus 4ac. Identify the coefficients of x squared, x, and the constant term. To avoid confusion, we will call them capital A, capital B, and capital C. Substitute into the discriminant equal to 0 and expand carefully. First substitution. Square and multiply. Simplify the product inside. Distribute the negative 4. Combine like terms to obtain a quadratic in the parameter a. Now solve this quadratic in the parameter a using the quadratic formula. Compute its discriminant. Apply the quadratic formula. Evaluate the square root and simplify both solutions. Therefore, the quadratic has a double root exactly for a equals 2 over 35, or a equals 2, or a equals 2. In this lesson, we will solve a neat parameter problem using the discriminant. We are given 3 expressions, x squared minus x minus 5, y squared plus 3y plus 3, and negative z squared minus 5z minus 5. We will find a single number, call it k, that all three expressions can equal, while x, y, and z are integers. Then we will solve for x, y, and z when that common value is found. Let us set each expression equal to k. Then move all terms to the left to view three quadratic equations equal to 0. These will have real integer solutions only if their discriminants are non-negative. Start with the first equation. The coefficients are equals 1, b equals -1, and c equals -5 minus k. The discriminant is 1 squared minus 4 times 1 times the quantity -5 minus k. That simplifies to 1 plus 20 plus 4k, which is at least 0. Therefore, 4k is at least -21, and k is greater than or equal to -21 over 4. Now the second equation. Here a equals 1, b equals 3, and c equals 3 minus k. The discriminant is 3 squared minus 4 times 1 times the quantity 3 minus k. That is 9 minus 12 plus 4k, at least 0. So 4k is at least 3, which gives k greater than or equal to 3 over 4. For the third equation, we first multiply by -1 to make it a standard upward opening quadratic. That gives z squared plus 5z plus 5 plus k equals 0, with it equals 1, b equals 5, and c equals 5 plus k. The discriminant is 25 minus 4 times 1 times the quantity 5 plus k. That is 25 minus 20 minus 4k, at least 0. So 5 is at least 4k, and k is less than or equal to 5 over 4. Combine all three conditions. We need k at least 3/4 and at most 5/4. The intersection interval is from 0.75 to 1.25. Since x, y, and z are integers, each expression evaluates to an integer, so the common value k must also be an integer. The only integer in this interval is 1. Now set k equal to 1 and solve each quadratic. For x, we have x squared minus x minus 6 equals 0, which factors as x minus 3 times x plus 2, giving x equals 3 or x equals -2. For y, we have y squared plus 3, y plus 2 equals 0, which factors as y plus 1 times y plus 2, giving y equals -1 or y equals -2. For z, we have z squared plus 5z plus 6 equals 0, which factors as z plus 2 times z plus 3, giving z equals -2 or z equals -3. Quick check. For x equals 3 or -2, the value of x squared minus x minus 5 is 1. For y equals -1 or -2, the value of y squared plus 3, y plus 3 is 1. For z equals -2 or -3, the value of -z squared minus 5z minus 5 is 1. Everything is consistent. Final answer. The common value is k equals 1. The integer solutions are x equals 3 or -2, y equals -1 or -2, and z equals -2 or -3. In this lesson, we will find all real values of x that make the fraction x divided by x squared minus 5x plus 7 an integer. We'll organize the work step by step and visualize the key ideas along the way. Step 1. Let the value of the fraction be the integer k. So we set x over x squared minus 5x plus 7 equal to k. Now multiply both sides by the denominator and gather terms. That gives kx squared minus the quantity 5k plus 1 times x plus 7k equals 0. We'll call this equation 1. By the way, the denominator never equals 0, so we will not lose or gain solutions from that constraint. Step 2. For real x to exist, the quadratic in equation 1 must have real roots, so its discriminant must be at least 0. Compute delta, the square of -5k plus 1, minus 4 times k times 7k. That simplifies to -3k squared plus 10k plus 1 is at least 0. Step 3. Solve the boundary equation -3, k squared plus 10k plus 1 equals 0. Using the quadratic formula, we get k equals the fraction 5 minus square root of 28 over 3, or the fraction 5 plus square root of 28 over 3. Numerically, that's about -0.09 up to 3.43. So the integer values of k allowed by the inequality are 0, 1, 2, and 3. Let's mark those on a number line. Step 4. Now solve equation 1 for each allowed k. For k equals 0, we get minus x equals 0, so x equals 0. For k equals 1, x squared minus 6x plus 7 equals 0, giving x equals 3 plus or minus square root 2. For k equals 2, 2x squared minus 11x plus 14 equals 0, with roots 7 over 2 and 2. Finally, for k equals 3, 3x squared minus 16x plus 21 equals 0, so x equals 3 and 7 over 3. Step 5. Collect all solutions. Our set is x equals 0, 3 plus square root 2, 3 minus square root 2, 7 over 2, 2, 3, and 7 over 3. As a quick check, plugging in x equals 3 makes the original fraction equal to 3, and plugging in x equals 7 over 3 also gives 3. Note that the denominator is always positive, so no solution is excluded by division by 0. Example: we are given a relation between the roots of a quadratic equation, x1 plus x2 plus x1 times x2 equals -1. If the equation has a double root, what is that root? We will solve this step by step using substitution and completing the square. Because the equation has a double root, the two roots are equal. Let R be that repeated root. So x1 equals x2 equals R. Substitute into the given relation. Combine like terms. 2r plus r squared equals -1. Move everything to one side to make a monic quadratic in R. Taking the square root of both sides gives r plus 1 equals 0. Therefore, r equals -1. This is the repeated root. To visualize a double root, consider the quadratic y equals open parenthesis x plus 1 close parenthesis squared. Its graph is a parabola that just touches the x-axis at x equals -1 and turns around. That touching point represents a repeated or multiplicity 2 root. Summary: using the given relation and the fact that a double root means x1 equals x2, we substituted r for both roots, simplified to the perfect square, r plus 1 squared equals 0, and concluded the double root is -1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.